HVAC 360, episode number 27. HVAC theory and heat transfer. Hey, welcome back everybody to another episode of HVAC 360. I'm your host, Matt Nelson. This week I'm going to be talking about kind of going back to school a little bit. I'm going to talk about HVAC theory. Specifically, I wanted to talk about heat transfer. You know, as I got into this, it was kind of the topic really ballooned on me. So I wanted to be able to just specifically talk about heat transfer and some of the important high points there. You know, I always say that HVAC is not really rocket science, you know, or specifically, it really doesn't have to be, you know. When you look at the field of HVAC, most of it is actually kind of already pre-digested for you. They boil it down to standard equations and things like that, and it doesn't really get into fine details unless you get into very specific situations, or you're dealing with, process HVAC, or you're dealing with a manufacturer who's kind of, doing that finite element analysis to be able to really dig down there, where they use the equations and the specialized software to get down into the nitty-gritty of HVAC. But in general, when you're talking about buildings, you're talking about standard things. So it all kind of gets boiled down to a couple different highlighted topics. And I wanted to be able to kind of just cover some of the concepts around heat transfer and what you learn, because really specifically when you go to the university and you learn about HVAC engineering, you really don't get a very laser-focused kind of course directed, because they really don't know what kind of career you're going into. You might go into the manufacturing path, or you might stay with building engineering. They're just not that sure, so they err on the side of caution, and they teach you as much as they can about as much as possible. But a lot of that you never really use. It's like kids in school growing up. They're like, are we ever going to use this math? Sometimes no, sometimes yes. I know that geometry to an accountant may not be all that applicable, but I certainly can relate to geometry in mathematics in what I do. So I guess what I want to cover here is just some of the basics of what I learned. We'll talk a little bit about that. Engineering really to me is more of an applied science, or science used in the real world. You really want to really want to boil down the concepts to something that's easy to remember, easy to learn. And the fact that really I can't go into too many details, because numbers don't translate at all to audio. So we're just, this may not be an episode for you, and but it's an episode for somebody, so you can understand me and forgive my indulgence of talking about such a basic subject. But I think that we need to start somewhere, and sometimes you really need maybe a refresher a little bit, or another way of looking at it. Maybe you're in that point in your career where you're actually teaching others, and you really have to come to some understanding, or another a better way of trying to teach it. So often when you're teaching something, it's hard to get down to somebody's level. If you're too technical, it goes right over their head. So you really need to boil it down to the basics when they're first beginning, because they really need to be able to grasp a concept before they start absorbing more and more information. So, and again, this episode, we're going to broad brush it, talk about concepts, and we're not really going to get into equations hardly at all. But when you talk about HVAC in school, unlike if unless you were in an architectural engineering program, which was another episode you can go and listen to, typically you're going to learn just about general HVAC type of applications. You're going to have typically you're going to have a course in heat transfer. You're going to have some a course in thermodynamics. and you're going to have something in fluids or fluid dynamics. So really, I'm just going to briefly touch on the fluids, and the thermodynamics I'm going to save for a completely different episode because, again, we don't really have the time to dive into that. But the thermodynamics, at least the way I envision it, is has to deal with more about cycles. And again, I'll cover that at a later date. So specifically, I wanted to hone in on this heat transfer. Now, heat transfer is, really, when I was thinking about it, I'm like, what's the best way to explain it to somebody? I guess heat transfer, most of us would be like, well, duh, it's the transfer of heat. But, think about it like this. I think if you think about heat transfer and the different facets of heat transfer, I liken it to the natural elements. You got earth, you got wind or air, you got water, and you got fire. I mean, really, those four elements, earth, air, wind, or earth, air, water, and fire, really are kind of they're a good descriptor of what HVAC heat transfer is. Because let's try to apply it to the three different areas. When you talk about heat transfer, you're going to be talking about conduction, you're going to be talking about convection, and you're going to be talking about radiation. Those are the three primary modes of heat transfer, or they're the three modes of heat transfer, really. So each of those actually applies to some of these natural elements. I apply when we talk about, conduction, this is by far the most important thing that you can learn. Really, you're obviously the others have some applicability, and the ramifications of non-understanding convection or radiation can be extremely harmful. But for the most part, the easiest of these concepts for people to understand is conduction. Now, conduction is really I liken that and I equate it to earth. And when I think conduction, I think of contact. I think of that, it's connection between two different materials. That's and the heat, the flow of heat transfer. Now, if you look it up in the dictionary, really conduction is defined as the transfer of heat between two parts of a stationary system caused by a temperature difference between the two parts. Now, the keys here. It's stationary. Again, when you talk mathematics, when you have things that are fixed or that aren't moving, all of a sudden the mathematics become a lot more easy to understand and to transfer into equations. So it's a static situation. Really, the universe loves fairness, and what I mean by that is it likes the temperature everywhere to be the same. So there's this force that drives, higher energy, higher temperature to a lower temperature. It doesn't necessarily have to be hot and cold. It just has to be a higher temperature to a lower temperature. And it'll do that, and it'll use these three forces of conduction, convection, and radiation to accomplish this. It really, you think about it. You think about a glass of, water. And you set a glass of water with ice cubes. You set it at the table. And eventually, by common sense that the ice is going to melt and that the water will eventually become room temperature. If you leave it overnight, it'll come to the same temperature as the surrounding air, so that you have that equilibrium that wants to take place, and you have heat transfer that basically goes from the glass and goes, actually from higher to lower energy. All the energy from the surrounding air is going to go into that glass and make that water warm up. Again, it's kind of like if you think about potential energy, or that's a totally different topic. But when you think about like a ball on the top of a hill, the ball will roll down the hill until it finds a place where the energy is the same. It'll rest in a valley, and it'll come to a stop. And when everything's at that static place, then you have equilibrium. Kind of the same thing happens with heat transfer. It'll go depending on how high or how steep that the differential is. It'll transfer faster, or it'll transfer slower if they're near equilibrium. But you're going to have that heat transfer between that higher energy state and that lower energy state. So let's talk a little bit more about conduction. Think about conduction. I guess maybe an easy analogy. Thinking about analogies here is think about a sandwich, and really conduction. When you think about a wall, conduction is like what's in the sandwich. It depends on how thick the materials are. It depends on what they're made out of. It depends on a lot of different factors. But conduction is like a sandwich because they're all kind of like squished together there, and you can think about it like that. You really are concerned about, I guess, two things when you talk about conduction and materials. When you're talking about the building envelope, you're really talking about the durability. Being able to resist the weather and just being able to maintain the structure. And the second thing is you want to be able to resist the transfer of heat. You spend an awful lot of energy, and you talk about energy efficiency. You spend an awful lot of energy just trying to keep a condition in a building, and you want to be able to maintain it. And to be able to maintain it, you're going to want to resist the external forces of the outside environment being able to affect that. So the better your wall is, the better that sandwich is between the inside and the outside, the better you're going to be able to control that inside environment. So heat transfer, obviously we can't really do anything about the durability, but the transfer of heat, that depends on a couple different factors. Some of it makes sense and is easy to understand, and others are a little bit more difficult topics to think about. You have, when you talk about heat transfer, the things that come into play are going to be the actual area that you're having. So you have to deal with area, how big the wall is, how big the window is. You're going to need to know a temperature difference. You're going to be able to, that determines, the rate of transfer. So if you have something that's 70 degrees inside and it's 70 degrees outside, guess what? It really doesn't matter what's in the sandwich. It really doesn't matter what's in between, because energy is not going to have any urge to transfer from one area to another. It's at equilibrium. But if it's 0 degrees outside and you're trying to maintain the inside at 65 degrees, now all of a sudden you have a 65 degree temperature differential. And I'm referencing Fahrenheit here, just off the cuff. So the temperature difference plays an important role. For those two factors, you have a tape measure. You can measure the area of things. That's very fundamental. And as a beginning engineer, that might be something that you're required to do, is just measure things. And you typically can identify either through standard conditions that you're using, or design conditions rather, or using a temperature gauge to be able to measure the outside temperature and the inside temperature. These are things that are, even non-engineers would understand and have a good handle on. The key is the resistance in the sandwich. That's really the key. That's why they pay you the big bucks. The resistance in the sandwich. You basically you talk about resistance in that sandwich. And resistance, is really, I think, the opposite of conductance. So, conductance, conduction, and this is what we're studying, and resistance, they're just kind of like two sides to the same coin. So when you talk about this conductance, you think of things that are good conductors and bad conductors. When you talk about good conductors, you think about things that are, even to kind of give you a better understanding, conduction and electricity. Electricity moving from a higher energy state to a lower energy state. That happens too. So anything that that easily transmits electricity would also be a good conductor for heat. even though it's kind of measured differently, this concept's still the same. You think about densely packed materials are good conductors. You think of copper, you think of aluminum, you think of other metals. Those things are very dense, and they conduct heat very well from one face of the sandwich to the other face of the sandwich. When you think about poor conductors or insulators, resistance, insulation, these are some of the words you're going to be using. The insulators, they're things that obviously don't conduct electricity well. Think about wood, you think about air, you think about glass, you think about brick. These are some of the things that are very resistant to heat transfer. When you combine a couple of things, I mean, think about it. If you look at the different insulators that are in the industry, you think about wool. That has a lot of air in there and a lot of natural fibers. You think of cellulose is another insulator that they use. Again, it's a combination of air and natural fibers. You think about fiberglass. That's actually glass and air. So it's really trying to get this this insulation value is this light kind of material. It's not the most durable, so it has to kind of be paired with something that's more resistive to the elements. And that's kind of part of the problem when you get something wet from conduction. It actually stops being an insulator and starts being more of a conductor. So it really doesn't do any good when you get insulation wet. But really, you're trying to get air or trying to get the molecules loosely packed, because that's what conduction is. It's molecules coming in contact, transferring that heat. It's one molecule bumping into another molecule. So if you can kind of space out those molecules, the transfer of heat is going to happen more slowly. Ultimately, when you think about the best insulators, a vacuum is a great insulator. It's really hard to maintain a vacuum, so it's not really the best. But I mean, if you look out there, there are products out there that are actually kind of for a better term, like a vacuum bag. I mean, it's kind of like a structure. It's like a pillow that has some internal rigidness to it, and then they pull a vacuum on it, and it takes out all the air. So it's a really great insulator for a very little thickness. Typically, they're going to use these for more of research applications when they're covering really cold temperature objects or some controlled environment. You couldn't necessarily use it today in the construction industry because as soon as you poke a hole in it, obviously all the insulation, talk about getting it wet, all that air rushes into that package, and it just becomes a very thin air barrier or a very thin air pocket in that sandwich that's resisting heat. So getting back to the kind of the equation, the area, the resistance, and the temperature difference, that actually takes you through what the heat transfer between two different spaces are, which is a basic one of the basic equations. So the resistance actually is measured in R value. You can also measure it in U, which is the inverse. It's 1 over R. And that's how resistance is measured. Now you can't measure or you can't add the U values together. That's Conduction 101. You can't add the U values together, but you can add the R values together. And it's similar to electrical circuits in that same way. So remember, when you're doing conversion, when you're adding the total resistance of a component together, don't forget to add the R values and not necessarily the U values. Of course, another thing that you got to remember is you got to make sure that you remember the inside and the outside air films. Now, these are actually what I kind of liken to the bread of the sandwich. They're the things that, are always going to be there. And they actually, they're very fixed numbers for the resistance, but it depends on the orientation. So if you know the horizontal numbers for a wall and the vertical numbers for a roof, you pretty much have it set. Sometimes you end up with an angle, and you have to get what the R values for those air films are at an angle. But for the most part, you're dealing with horizontal and vertical lines. Again, it's a much simplified form. So really, when you talk about conduction, this is really going to be your basis of your load calculations. For load calculations, heating is pretty much easy because, again, everything, you take out the variables in the system, you know what the temperature differential is, and you know what the sandwich is and everything like that, so it becomes very easy. When you talk about cooling, it becomes a little bit different because you throw in the sun into the factor. Obviously you can't ignore the sun when you're dealing with cooling loads, and since it changes position based on the time of day and based on the and the temperature difference during the season, it's really kind of hard to simplify that. Of course, they have engineers in the past have had design days, and they've gone through the calculations with the different various factors. So they have done a little bit of that already. But now, typically, that's where you're going to use load calculation software is doing that. So let's talk a little bit about convection. Now, convection is, you can equate that, if we're using our natural elements analogy, that's the air and water. And again, I think that literally translates pretty well to how you transfer the heat. When I think of convection, I think of flow. The definition, if you're to look at it, is the transfer of heat by the circulation or movement of the heated parts of a liquid or gas. Now, remember the conduction was, more of a static. This is actually, it has circulation and movement of the heated parts of some sort of fluid. So that's really what convection is. Now, when we talk about convection, we got to think about capacitance. Now, that's capacitance again. That's the amount of energy that's stored, that you're able to store in a certain fluid. So, even though air is an insulator, water, but air is an insulator, but it's one of those things where you don't have to waste a lot of efficiency, translating it. Air is all around us. We can heat it. We can cool it. Even though it's an insulator, it still has the ability to retain heat or retain, to reduce the temperature, reduce the heat of that, to absorb heat from its surrounding as kind of the cooling effect. You have water, and water has a very high capacitance. Again, because it has kind of the dense storage of the molecules, you can store a lot of water. If you keep putting energy into water, you get steam. So steam is also another medium in which you can store a lot of energy. If you want to think about kind of the capacitance of air, think about you think about sitting outside, and one day it's 75 degrees Fahrenheit, and it's sunny out, and it's really dry, and it just feels just perfect. Now, you translate that into 75 and really muggy. Now there's moisture in the air. You're not able to kind of feel comfortable or reject the heat, so that becomes kind of a problem for you. Now, if it was 75 degrees and you were in water, again, because of equilibrium, you're going to continually draw that heat out of your body, and it's going to feel cold. It's going to be like a swimming pool. How when you first go in there, it's really, really cool. That's because there's all this capacitance around you that can draw that heat and store that heat. So those are the kind of things that you can think about when you think about capacitance of this fluid that you're using when you're talking about convection. Obviously, one of the great things about HVAC, again, you get it simplified and boiled down to those finite elements. We use air and water. I mean, we might add some things to water to change its properties, but typically we're going to be using standard air and water conditions. So that simplifies a lot of the complex equations that you find in convection very, very nicely. And obviously, two of the fluids we use, not only because they're all around us, it's an abundance. You don't have to, buy air or pump air in this case. Water, that might be a little bit of a different animal, but still relative abundance, at least for now, 2011. So that's great. Obviously, another way to move energy around in a system is to use refrigerant. I'm just going to state that, not going to go into it at all, but I think that I'll talk more about that in another episode. So when you talk about convection, you're really talking about some fluid dynamics. That's another course that you take in college, but when I think about movement, I think about fluid, and I think about laminar flow, which is kind of like smooth flow, and there's not a lot of churning or movement. Think about like a slow stream, just kind of moving down a river or a water down a stream or whatever. You get the picture. The other, the other opposite of laminar is the turbulent flow, where everything's being churned up and mixing. These are other vital components in a system, and it's really often critical to know, and typically it's intuitive. You're not calculating it per se, but intuitive to know where you're going to have turbulent fluids or where you're going to have laminar fluids, because that's really going to impact the resistance to that flow. You talk about another thing in fluid dynamics, and when you talk about laminar or turbulent, you talk about a Reynolds number. I'm just going to throw that out there. I'm not going to explain it too much, but again, a Reynolds number will kind of tell you whether or not a fluid is in a laminar condition or it's very turbulent. But the fluid dynamics really relates to the resistance of the flow, the transfer of heat, and the power required to move the fluid. When you have a turbulent flow, sometimes they'll put what they call turbulators on a coil, air conditioning coil, that actually increases the surface area, the transfer of heat, and it mixes the air quickly. So when you talk about laminar flow, you don't necessarily get the best transfer of heat, but it does take less power. If you're pushing something and it's going smoothly through a pipe or a duct, it does take less energy. Again, we talk about standard conditions. These can typically be reduced to simple charts to keep it simple. But this is a situation where if you're in other industries, or you're the gas and oil industry, you're in mining industry, you're in the chemical processing industry, you can really get very, very complicated with the different types of fluids that you end up pumping around the system. It really gets into more of the computational fluid dynamics software that you use. But again, if you're dealing with HVAC, you're dealing with building systems, you're dealing with standard air and water, you don't have to get into a lot of that complex analysis. So convection, when used in design, you typically are going to be talking about, say fin tube. You're going to be talking about discharge air temperature and how it comes out of a diffuser, or how you are heating and cooling a space. It really you really don't have to get into too much of the fine details when you talk about convection in the HVAC system. You really just need to know. It's more important to know how the equipment works more than you need to know okay, well, I have to calculate the convective force off of fin tube. No, you just need to know that fin tube puts out a certain amount of BTUs that counteracts the conductive effect of the space in your load calculation. You just say, okay, well, it works. I don't have to make sure that just as long as you know that the convection is happening. You don't really have to know how, you just want to make sure, okay, well, if you're going to have fin tube and it's going to be up against the outside wall, I want to have, furniture, I want to have just a kind of a path for air to flow around that, because you know that if it doesn't have a path to flow around that, it's just going to, end up getting hotter and hotter. It can't use convection, the convective forces, to be able to transfer that heat to the air to get it to the space where you need it. So again, you're looking at the concept of convection around a piece of equipment and understanding that and kind of enabling that, rather than being very specific about calculating the convective forces of a particular piece of equipment. Other things that you can think about is the efficiencies. That a cooling coil transfers so much heat because based on the temperature difference, the difference of the incoming water, the incoming air, that through the charts and the graphs of the manufacturer, what that is, and you can analyze that. They'll have certain efficiency factors in the pumping equipment, so it can simplify and you can understand, okay, how much of the energy is being transferred, how much can I get to the space, what is it best used for. So that's really, when you talk about convection, there's a lot of things that are going on, but you don't need to know the nitty-gritty details. Now, if we want to take it up another notch, the third area is radiation. Now, radiation is one of these things that I've personally found a little bit. The concept is easy, the application and the numbers part of it, is getting rather difficult. But if we go back to our natural elements analogy, this is going to be fire. We're going to equate it to fire. Think about it as being like the sun. The sun that's a very kind of a good radiation type of process. The definition: radiation, the complete process in which energy is emitted by one body, transmitted through an intervening medium or space, and absorbed by another body. Now, the key to radiation, the key concept to the radiation, is that distance plays a key role. But that the energy really transfers from one body to another body, and that there isn't really, it doesn't transfer to that intermediate space. It doesn't transfer to heat the air. Radiation just goes from one area into another area. And obviously the closer that you are in talking about distance, the closer that you are, the more energy gets transferred to you. It's just like a light. You hold the light closer, it gets arithmetically brighter. I think it's the cubed root or whatever, if you gonna get technical. But and if it goes further away, it just gets it gets that much dimmer. But the same thing with the radiative process. Again, when you talk about radiation, you don't need to know all the numbers, because most of the manufacturers have calculated the optimal distance that you need to have and of their equipment from surface to surface to get the amount of heat that you need at that particular location. So really, they've simplified it quite a bit. Again, just as convection, you need to know more about the equipment and how the equipment operates, and following the manufacturer's recommendation. That's what you need to know about radiation. You don't necessarily need to know okay, how do I calculate the radiation of a black body, or how the different concepts that you'd learn in school. That's really kind of going beyond what you need to know. HVAC is vastly simplified, from that concept. All right. Well, again, in general, we've covered topics of heat transfer. We've talked about conduction, we've talked about convection, and we've talked about radiation. Those are the three forces that you need to focus on. And really, if you're gonna learn something, focus on the conduction. That's going to have the most bang for your buck as far as your learning goes. A lot of things have to deal with that. So again, HVAC is not rocket science. And I think that a little time and attention, and you can learn quite a bit about it. So to wrap this up, I appreciate you listening, every one of you. I really appreciate you've stuck through it through the half an hour here or so, and I really appreciate you listening. If you found this useful, please let somebody else know. Share it with somebody else. If you have any comments or tips, please let me know. You can reach me at matt@buildingx.co. Or if you want, just sign up for the newsletter. You get some of the information that you have, some inside information, and it kind of alarms you as to what topics we've been talking about, some upcoming topics that we've been doing. So it's kind of valuable. You can just go to buildingx.co and sign up for it there right on the front page. So, also, let's see. That's pretty much it. If you want to follow me on Twitter or on, you want to contact me or connect with me on LinkedIn, go ahead. Twitter is @BuildingX, and LinkedIn, you can find me. You can find me. So I think it's a Matt Nelson PE. And that's kind of the public page that I have. So you can friend me up from there, or you can find me. Just search for me, HVAC 360. You probably get pretty close. So again, thank everyone. And just as a side note, I'd like to dedicate this episode to my father. So, all right. After all, everybody, remember, know what you build and share what you know.